All right, so I'm Jerome Jennings, product manager for the mechanicals. I'm going to walk the SPX reps and SPX personnel through some of the differentiation of the various mechanical products. So I'm going to start with the gearboxes. Here on the right is a Marley gear reducer. This is a Series 36 for a typical power application, very common in the field. And over here would be an Amarillo. This is their A36, so it's a footprint equivalent to the Marley, but we'll walk through some differentiation and show that it's far from equivalent in terms of performance and features. So one of the first things that I want to point out when you first look at these boxes is you'll notice on the Marley there's a lot of external finning here, all the way on the side, also on the back. There's actually 47% more surface area on this Marley gear reducer than you see over on the Amarillo here, which is very flat-sided, very boxy, doesn't have nearly the surface area. So when you've got all that air coming up from underneath your fan through the cooling tower, you're rejecting a lot more heat with the Marley box versus the Amarillo. So that's one critical differentiator. Another thing I want to point out with the Marley gear reducer is the large oil ports that we have. So as this pinion shaft down here, as it's rotating inside the box, there's actually an oil slinger here. It's not shown, but there's a large disc shape, and as that's rotating inside this region of the box, it's actually flinging the oil up into these cavities. And there's a large oil trough right here, as you can see. This is a very generous size. I can actually put my entire finger through there, and it actually comes out through a port here on the side that feeds the pinion cage. So again, huge hole. This allows a good fresh oil to flow throughout the box and keep it lubricated and keep it running cool. Also another port up here on top that feeds some of these other interstage bearings. You can see a large hole here, and it works its way through the box and feeds the upper fan shaft bearing as well. So significant port sizes to keep oil moving. If you look at the Amarillo design, and this may be a little bit too dark to see, but really the only port they have feeding their pinion is right here. It's very small, kind of dark. I don't know if you can see that, but that's the only thing feeding their pinion. So they have a similar slinger design, bringing oil up, spills into this cavity reservoir, but it can only really get through this one small hole, through that small hole into the pinion bearing. So significantly smaller bearing or port sizes. All right, another feature here is we talked about the oil ports on the inside of the box. This is actually the large holes on the pinion cage itself. So these holes are mating up with that large hole on the case of the box. So it gives good oil flow into this pinion cage to get to the pinion bearings. So another nice advantage of the Marley gear reducer. Another thing I want to talk about is the bearing size. Marley's long been known for their bearing life, and here's actually a couple bearings we use in our box. This is a double row bearing for this happens to be I think this is the lower interstage bearing. And then we also use a massive, and this thing's heavy, it's probably 30-40 pound bearing for the upper interstage. So you can see these are very beefy bearings, very heavy duty. If you come over to the Amarillo box, here's their bearing. They're using just a single row for their lower and upper interstage bearings. So significant difference there. If I bring them over, I mean that's quite a difference. I mean Marley's using very beefy bearings, so that's what gives us the 100,000 hour bearing life, and also contributes to higher bearing life, particularly on the interstage shaft, which is normally mounted as the shaft connected to the pinion in this region. So these bearings will actually give you about 3 times more life than the equivalent Amarillo bearings on their interstage shaft. So definite difference there. Okay, the other thing I want to hit on is the pinion shaft here again. Notice that the Marley pinion shaft is all one single piece. It's one big hunk of metal. You know, it's a significant chunk. The gear itself is integral with the pinion shaft. It's all one big hunk of metal, so it's got a really strong product. If you come over to the Amarillo design, which is a little bit back here in the corner, you can see that there's actually multiple pieces. So you have the shaft, but then the head of the gear is a separate piece. So it's actually got to be keyed onto that shaft, and then there's a lock washer and lock nut on the back side to keep it all together. So you got multiple pieces. You're going to have a little bit of tolerances there. You're going to have a little bit of vibration, a little more sound occurring because of those interactions versus having a single one-piece pinion. Finally, in terms of sound, the Marley gear reducer's got 80% less sound, and that's been proven in actual third-party tests. So moving from gearboxes, we'll jump into drive shafts. So we can see here we've got the Marley composite drive shaft, Comp DS, versus an Addix drive shaft over here on the right. Now these are for different applications. This one's probably for lower horsepower, which is why it's smaller. But some of the key differentiators here are the hub itself. So this is a S316 billet that's been machined down, so it's a very consistent granular structure. There's no porosity in there. Very strong piece. The hub of the Addix drive shaft is actually cast. It's a cast S316. Sometimes you'll see a CF8M call out on some of the specs for the Addix. That means it's a casted version. So casting has a little bit more porosity, potentials for inclusions, etc. So billet's a stronger piece. Also, in terms of the tube, Marley uses UV inhibitors inside of the tube as part of the resin. So that actually gives you longer life in high sunlight conditions, whereas the Addix is not using UV inhibitors, and it actually tests at the SPX Research and Development Center has shown that you have significantly longer life before any kind of degradation occurs for that tube. Another feature of the Marley versus Addix drive shaft is actually the flex element. So here you can see the Addix flex element design versus the Marley design. So if we go ahead and take a look at the Addix design real quick, you can see it's a single piece. It's got some bushings in here where the hardware mounts, and there's a little piece here that we took apart, but inside of this thing is a little dog bone pieces that are laid in, and they're actually constructed of fiberglass material that are stacked up, and then it's all urethane coated. So that's the Addix design. When we look at the Marley design for the Comp DS, this is actually a single piece, very similar. And again, this is larger just because there's a difference in application here. But this is all urethane coated as well. And on the inside, it actually has carbon fiber pieces. And here's an example of that here. So these carbon fiber sheets are stacked up with inside of this flex element. Carbon fiber is lighter and stronger per unit weight than the fiberglass used in the Addix drive shaft flex elements. Moving on to the fan blades, we've got here a Hudson Toughlight 2, which is the blue blade, Hudson Toughlight 3, which is the white blade, and then the Marley HP 7000, which is the gray blade over here. So when we talk about these colors, blue and white for the Hudson, that's actually because they paint a layer of paint onto these blades after the manufacturing process. So it makes the blades look nice coming out of the factory. However, it's a coating that can flake off, crack over time, and then once it's gone, it can leave your blade exposed to sunlight, moisture, etc. The difference with the Marley blade is that it's gray, but it's not paint. It's actually a pigment that is infused into the resin during the process. So as the resin is going throughout the fibers in the mold, it's got that gray color with it. So no need for painting afterwards, and it's not going to flake off over time because it's infused within the part. Another thing you'll notice here is that the Hudson blade, particularly the Toughlight 2s, which are very common in the field, are actually two pieces. So they have the main shank portion, and then they have kind of a rubber boot here with a mechanical joint going to the rest of the blade. Obviously you have some stress concentrations that can build up there, which is a concern. Hudson's changed that with the Toughlight 3. They've gone to more of a single piece, like the Marley has been for many years. So with that, the blade also has some strength characteristics. In particular, the HP 7000 design here has a very large shank. I don't know if you can see that on film here, but we've got about a 8.25, 8.5 inch shank on the Marley HP 7000, 8.5 inch, versus the Hudsons here that are only 6.25 inch in diameter. So that gives a lot more strength to the blade, especially as it's being clamped into the hub. It allows that force to spread out and gives a longer lasting blade. So another thing about strength is the orientation of the fibers within the blade. And we actually proof load all the Marley HP 7000 blades, particularly on the larger sizes. When you get up to a certain diameter and above, these are all proof loaded, and they have to pass at the factory. They get loaded. They get set in a device and loaded, and they have to surpass 1,100 pounds of buckling force. So these blades survive that. They actually can survive up to about 1,300, 1,250 pounds of buckling force, whereas the Hudson Tough Light 3 here can only handle about 850 pounds, and the Tough Light 2 about 900 pounds. So these Hudson blades wouldn't even pass our standard Marley criteria for buckling strength. Also, when we look up at the tips of the blades, so we've got the shank portion and the root of the blade here, and we've got the tips up above. So one of the things you'll notice is that on both of these Hudson designs, they actually continue to taper all the way to the tip. Whereas the Marley has a patented, marketed flare tip design. So this is actually trademarked, is what I wanted to say. Trademark flare tip that actually goes out right at the blade tip. So as that fan blade's passing inside that fan cylinder, it's capturing that last bit of air before it wants to drop off the blade and getting it directed up and out the cylinder. So that helps with efficiency and performance. Finally, erosion resistance. The HP 7000, on the leading edges of all these blades, there is a protective strip. And in the Marley design, we use a nylon barrier strip. So all those moisture particles that are coming up through the cooling towers, they're hitting and impacting that front edge of the blade. A nylon barrier strip is going to give you very long life in that kind of condition. Whereas these Hudson blades are using a different type of material. They call it the Tough Edge, aluminosilica. And we've actually done tests at the SPX Research Development Center that shows that our leading edge, the Marley leading edge, loses a lot less material over time in those kind of conditions. Another thing is with the gear reducer versus the Amarillo A36 is the shims. And with the Marley design, we actually use metallic steel shims. So these are actual steel to keep all your different settings with your gears and your bearings. You use the shims to get those proper clearances, and we use metal. Amarillo, when we tore this box down, found out they're just using plastic. You can see these colored plastic shims. They're quite a bit flimsier for one, but over time with heat and temperature and moisture, I mean, you're going to have some potential creep here as the plastic will want to deform and change shape. So you could lose a few thousandths in tolerance and gear settings. So that could be a concern. It could lead to a noisier gearbox, and it could also lead to more heat generation, and it could also lead to less life. So very critical. Okay, this is our F400 counterflow setup, side by side with the F600 crossflow setup. So we wanted to show some of the distribution setup and fill and eliminators within a cooling tower. So for the F400 counterflow, you can see this is simulating the main header pipe here. So a large amount of water will be flowing through this, and it flows into the lateral pipe. This particular one's an 8-inch diameter, and then it feeds the branch arms into the nozzles. So we've just got a few different examples of nozzles. You probably wouldn't have this type of setup in a normal cooling tower, obviously, because they're all different orifice sizes, but just shown for example. So this is our NS6 counterflow nozzle, so it can flow a very large amount of water. You can actually pass a golf ball through this thing if you wanted to, with our NS5s right next to it. So color coded for the different orifice sizes that may be used on our given cooling tower. So as the water's flowing through these nozzles, it's then going over the fill. This particular fill is the Marley DF254, which is a low clog fill. And then as the water passes down through that fill, it's then dropped into the basin. Here's some different types of fill we have, just for an example. NC20 is a very low clog fill. VC25. We also have MC75, which is a very high performance fill. And pretty much everything in between. I mean, we could do high performance fill, or we can do extreme low fouling. That's always the sacrifice with performance versus fouling. And then finally, as that water's passing through the fill, and you've got all this air rushing up through the tower in a counterflow application, the Marley TU drift eliminators up here that would be positioned above the spray system are going to capture those moisture particles and keep them in the tower. So it's got a 3-pass system, 3 different angles to allow the particles to hit the sides of these eliminators and then drop back into the tower, minimize the drift coming out. And in the crossflow setup, like you'd see in a Marley F600, it's a little different setup. Instead of a piping system, you'd have some type of gravity basin. So this would be filled with water, and inside of there are actual nozzles that are little spiral target nozzles. So as that water has a certain amount of head, it's going to drop down through these nozzles, hit this daisy, and splash down over a fill media. And in this case, for the cross-flow towers, it's typically a splash fill as opposed to the film fill we saw earlier with the F400. So with splash fill, you usually have some type of bar. Here we've got examples of our Marley Mesa bar, Marley Omega bar, and there's lots of other varieties. There's a V bar shown down here. So those bars are providing a surface for the water to splash on, hit, and try to atomize and spread and propagate down through the fill. In order to do that, they're supported by some type of grid system. This is our Marley Gridlock, again trademarked gridlock structure. You know, it's a very injection molded process to produce it. Pretty lightweight and but yet strong and can support a lot of bars. And then finally, we've got the cross-flow TU eliminators, which prevent water particles from again exiting the fill area, coming into the plenum area, and wanting to fly through the fan region. So again, 3-pass system, and then they have these holes so that after that water's trapped, it can drain back and drain into the tower. Okay, and another nice feature of the cooling towers now that Marley's developed is this new firewall piece. So it's a single piece sheet that can be very large and screwed into place, and it's superior to a lot of the previous product that's been out there on the market, which can absorb moisture, fall apart, become break down. This product is very robust, very strong, passes all the firewall certification for fire propagation, and is really a unique product for us. And we also have some simulation here of what the casing could look like as well within a cooling tower.